You're not sharing your screen yet, just so you know.
Yeah, I know.
Okay.
Now I'm gonna hit share screen. And slideshow. Current slide. Okay, I think we're ready. You ready to start us off?
Sure, just anytime.
Well, no. Oh, here we go. Soup and salad special.
Okay, go back and we'll start.
Just from a blank screen?
Yeah.
Okay. All right, so welcome back, everybody. We're going to be starting section 4.4 right now, which is on permutations and combinations, just different techniques for counting all different types of possibilities.
Yeah.
So Karen's going to get us started off with a beginning example.
Yeah, so this is just like a quick little intro example. So let's say, for example, that you go to a restaurant and they have some sort of soup and salad special where they give you a list of soups and salads and you're allowed to pick one of each. Okay, so let's see what our options are here for my fake restaurant. So for soups, let's see, we have options of broccoli, cheese, potato, or tortilla. Salads, you can choose from a house salad or Caesar salad. And the goal here is for us to figure out how many possibilities there are. Okay, so let's see what sort of pairings we can put together. So we could pair together broccoli cheese with a house salad, broccoli cheese with a Caesar salad, potato with a house salad, potato with a Caesar salad, or tortilla with a house salad and tortilla with a Caesar salad. Okay, so we were able to easily, list these out by hand, count them up, and we can see that there are 6 possibilities. Now, Dr. Insko, can you figure out a way for us to get the same answer, but in some sort of mathematical way?
Sure, you would look at the number of possibilities for the green letters, which there are 3, and then the number of possibilities for the purple letters, and there are 2. So 3 times 2 gives you 6 possibilities.
Yeah, exactly. So instead of listing them all out, one way that we could have done this was just to count however many options we had for soups, however many options we had for salads. We multiply those 2 numbers together, and we still get the same final answer. So that right there is an example of the fundamental counting principle, or sometimes it's called the fundamental counting rule. Okay, so what we just illustrated was that in a sequence of n events, in which the first event has k1 possibilities, the second event has k2, the third has k3, and so forth, then the total number of possibilities of that sequence will just be all of those amounts multiplied together. So k1 times k2 times k3, up to however many options that you have.
Right, so number of soups times number of salads and so on.
Exactly.
Cool. So I guess I'll take over for example 1. It says a paint manufacturer wishes to manufacture several different paints. The categories include the following. How many different kinds of paint can be made if you select one color, one type, one texture, and one use? So for colors, we have red, blue, white, green, black, brown, and yellow. So how many is that? 7?
Yes.
6, 7, okay. Latex and oil are the 2 types. And then texture is flat, semi-gloss, or high gloss. And then uses are for outdoor and indoor. So how many different types of paint can we select? Well, it looks like we have, let me count that, that's 7, right? That's 7 different types for colors, 2 for types, and then 3 for textures, and 2 for uses. And so multiply all those together and you get 84 different kinds of paint that you could order from the paint store. Any questions on that? No?
Not for me.
All right. Do you want to do example 2?
Sure. So it says that a license plate has 4 digits. How many plates can be issued, assuming that repetitions are allowed? Okay, and as far as digits, we're talking about the numbers 0 through 9 that you're allowed to put in for each one. Okay, so we can view this as a sequence of events where we need to pick a digit for each, or pick a number, let's say, for each one of those spots on the plate. Okay, so I can kind of lay this out as like digit 1, digit 2, digit 3, digit 4. If you could just click for me. Thank
All right.
you. Okay, so the numbers 0 through 9, that's 10 numbers. So we have 10 options for what can go into digit 1. And then since we're allowed to repeat, I also have 10 options for what can go into the second digit, 10 for the third, and 10 for the fourth. And then the fundamental counting principle says that we just need to multiply all of those 10s together. So 10 times 10 times 10 times 10 gives us a total of 10,000 different plates. Now, what if repetition is not allowed? Well, for that first digit, we still have 10 options. We have the numbers 0 through 9 that we can put there. But now that we've used 1 and we're not allowed to repeat it, we only have 9 options left for what can go in the second digit, and then 8 digits or 8 numbers for the third, and then 7 for the fourth. So we drop it down by 1 each time, and then 10 times 9 times 8 times 7 gives us 5,040 different plates.
It's funny how getting rid of repetition cuts the number basically in half.
Yep.
Okay, so for example 3, it says a business owner wants to rank her 5 locations according to a certain criteria. How many different ways can she rank the 5 locations? So there's 5 locations, and so she has 5 options for the first location, like what she wants to rank number 1. And then because she's used 1 again, she can only have 4. And then I think you can predict it's going to go 3, 2, and 1. And so that's 5 times 4 times 3 times 2 and times 1 is 120 different ways that she could rank them. But what if she only wanted to rank the first 3 locations, or the top 3 locations? Well, again, it's the same start. It goes, you have 5 options for the first one, 4, and then 3 for the second. And so this time you only get 60 ways to rank the top 3. And I think that's a preview of the next rule that we're going to see. Nope, it's a preview of factorial notation.
Yeah, so before we get into the permutation rule, we're going to need to know the notation for factorials. So factorial notation is just where you use an exclamation point, and the formula is that if you have like n factorial, it means you take n times n minus 1 times n minus 2 all the way down until you get to the number 1, and you just multiply all of those together. So I think I have a little example there, like 5 factorial just means that you do 5 times 4 times 3 times 2 times 1. So it's just, you take whatever the number is, you multiply it with all of the numbers lower than it all the way down to 1. So that's all a factorial means. And just by definition, 0 factorial has to equal 1 in order for that to work.
Yeah,
okay,
so like factorial is like the just notation for the number of permutations of n objects. And so the reason why 0 factorial is 1 is how many ways are there to arrange 0 objects? Well, there's one way to do that. You just don't do it, right?
Yeah.
Makes sense. It also makes the formula work, but if you think of it as like arrangements of something, there's one arrangement of nothing, just as there's one arrangement of one thing. Okay. Sorry, so you can keep going now. I just wanted to interject.
Okay, so our first main rule that we're going to look at today is the permutation rule, and this is going to be an arrangement of n objects in a specific order. Okay, so kind of what you want to learn to memorize, like the key phrases are that a permutation is where order matters. Okay, and this also kind of goes with distinct roles, or that there's some sort of ranking. So in some questions, like with the applications, it'll make sense to talk about order. In other applications, you know, if you see any sort of distinct roles or distinct sort of like ranking system, that also tells you that you're working with a permutation. So there's going to be 2 main permutation rules. The first one we're going to look at here is where you just have n objects you're permuting n objects using R objects at a time. Okay, so for example, let's just do like a little easy one here. Let's say that I want to permute the letters A, B, C. So what are all the different orders I can put those letters in? Well, I could do A, B, C, A, C, B, B, A, C, B, C, A, what else? C, A, B, and C, B, A. So there we have a total of 6 permutations. Now, the actual formula for this and the notation is going to be NPR. So we use a capital P to denote a permutation. and then like the N and R are like little subscripts. And the formula is N factorial over N minus R factorial. Okay, so N is the total number of objects, R is however many you're permuting at a time. You just plug those into the formula and simplify it out. So let's do an example.
So for this ABC example, the N was 3 and the R was 3, right?
Correct.
So in this case, you got 3 factorial on top, which is 6, and on the bottom you got 3 minus 3 factorial at 0 factorial, which is 1. So you end up getting 6 over 1 in that case. So it worked out in this case anyways. Okay, so now we have example 4. It says a radio talk show host can select 3 of 6 special guests for her program. The order of appearance of the guests is important. How many different ways can this be done? So now here, the key words here are that order matters, which Karen has highlighted with the PowerPoint. And N is going to be what? 6. R is going to be 3 because we have 3 guests. And so if you're just thinking about this, you could do like what we did before, where you just go 6 times 5 times 4, and that would give you the right numbers, right? Or you can use this formula, which is 6 factorial over 6 minus 3 factorial. And then when you write out what those notations are, you get 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. And so then you can cross out the 3s, the 2s, and the 1s, and you get that same formula that we did in our head before, like 120 different ways. And so that was kind of like, what did I just say? Oh, we haven't done an example where we did 6 factorial. We did 5 times 4 times 3 times 2 times 1, which also happens to be 120, right? No? Okay.
Yeah, that makes sense because the 3 and the 2 went away, which is the same thing as 6.
Yeah. Okay, and then you were going to say something about the fundamental counting principle, which I think is what we just said here.
Yeah, and that's what you actually mentioned right at the beginning there. So an alternative way of answering this question is to just view it as a sequence of events where, you know, your first event is going to be picking whatever guest comes out first, and then whoever comes out second, and then whoever comes out third. So when you go to pick the first guest, you have the 6 options, and then once you've selected one, now you have 5 left over, and then you have 4 for the third guest for the program. So either way, you end up doing 6 times 5 times 4 and getting 120. So just the idea here is that with a lot of these questions, you know, you might read it and be like, oh, okay, that's a permutation. I want to use 6p3. The person next to you might read it and their instinct might be, okay, that's a, you know, a sequence of events. I think it makes sense to do, you know, 6 times 5 times 4. Either way is correct, and either way you'll get the same answer.
Cool.
And then we did just want to point out that you don't actually have to do the formula by hand. I mean, that's a pretty easy one to do and, you know, write it out, but the numbers can get pretty large. So there is a way to do this in your calculator. So I don't have it, I don't show every step on the PowerPoint, but if you click math, the math button on your calculator, which is right below alpha, click math and then go over to probability. It's either PROB or PRB, just depending on which calculator you have. And then you'll see that option 2 is NPR. Okay, so if you are using the 83 calculators, what you have to do is actually type your N in first. So you would type 6. Then you would go to math, go over to probability, go down, select NPR, and then you type 3. Then you'll get 120. If you're using the 84 calculator or the one on your computer, you can go straight to math, go over to probability, go select the NPR, and then it's going to give you like little empty boxes for the N and the R, and you're just going to fill those in. So 83s, you have to type the N first. 84s, you can just go get that NPR function and then fill it in.
Cool. Thanks, Karen. This seems to be a repeat of our previous slide.
Well, so a few of those examples that we already did can actually also be answered with permutations. So the fundamental counting principle, wait, how do I want to say this correctly? So every every permutation problem can also be answered using the fundamental counting principle, as long as there's no repetition. So if we look back at the ones where we use the fundamental counting principle, as long as repetition is not allowed, then we can also answer this in terms of permutations. So the first one, 2A, repetition was allowed. So the only way we could do that is with the fundamental counting principle. But on part B, where repetition wasn't allowed, basically what we're doing is we're taking those 10 total digits and we're permuting 4 of them. So another way of answering part B, if you can just click for me once, is 10p4.
Yep.
So that'll get you the same answer. On 3A, there was no repetition. Okay, we had the 5 locations and we were basically permuting all 5 of them. So you would get the same answer if you did 5p5. And then for part B, we had the 5 locations and we were only permuting the top 3. So another way of answering that one would be 5p3.
Perfect. Okay. Okay, so then the next rule that we're going to use is the Permutation Rule 2. And this is where before we had n objects and we're permuting r of them. Now it's saying that we have n objects and r1 of them are identical, r2 of them are identical, up to r sub p of them are identical. So this is probably best explained with an example. But here's, we're permuting a bunch of things, but some of them are in the same class. And so a good example of this is like the permutations of the letters in food. Okay, so there are 4 letters there. So if we could distinguish the O's, then we would have 4 factorial different permutations. But if we don't label or we can't color the O's and we can't tell them apart, then those 2 permutations of the word food are exactly the same. So we need to divide out by the number of permutations of the O's because they look exactly the same. We can't distinguish them. A lot of times when I teach this, I'll make one O like large and one a lower O. And then you say, if you just forget about capitalization or whatever, you get the same word. So that's why we're dividing by 2. So to count the number of permutations of the word food, you would take 4 factorial, and then you would divide by 2 factorial, and then also 1 factorial and 1 factorial, which is just dividing by 1, which doesn't change anything. Where the 1 factorial is the number of F's and the number of D's. So in notation on the right, we have n factorial over r sub 1 factorial times r sub 2 factorial times dot, dot, dot up to r sub p factorial. So for this one example, it would be 4 factorial divided by 2 factorial divided by 1 factorial divided by 1 factorial, which would, of course, would give you 4 factorial is 24 divided by 2 is 12. So there are 12 permutations of the word food. Is that correct?
Sure.
Okay. Yeah, that seems right to me. Okay, so for then example 5, do you want to do this one, Karen?
Yeah, so it says how many permutations of the letters can be made from the word statistics. Okay, so the n that's on top in that formula is the total number of letters or total number of things that you're permuting. So if you count those up in statistics, there's 10 total letters. Now what you want to do is go through and like just count however many of each letter there are. So let's see, there are 2 or 3 S's. T's, there's 3 of them as well. And then just go through all of them. So there's 1 A, 2 I's, and 1 C. Okay, now those are all of your R's. So if you want to label them for yourself, you know, you can do that. So R1, R2, R3, R4, up to R5 there. So when you go to plug them in the formula, it's just going to be 10 factorial over 3 factorial times 3 factorial times 1 factorial times 2 factorial times 1 factorial. And unfortunately, there's not like an easy way to have your calculator do this formula for you. So you do have to actually do this one out yourself. But you can still, like at this point, type it in your calculator. So if you go to that same place where I told you that NPR was, you'll notice that the 4th option down, so if you go to math, go over to probability, there's the 4th one down is the exclamation point. So that's your factorial key. So you can type 10, go get that factorial key, then divide. And then just the main thing to remember is that for your denominator, you have to put parentheses around the entire thing. So you want to open a parentheses, type 3, go get the factorial, type another 3, go get the factorial. It is kind of time consuming. But to kind of help you with time a little bit, you can leave off 1 factorial, since dividing by 1 isn't going to change anything. And then with some of these, I mean, 3 factorial just means 3 times 2 times 1. So if you wanted, you could just, you know, kind of do that in your head and know that that's 6. So it's kind of up to you how you want to do it and what you choose to type in your calculator. But you can make sure that your calculator just kind of matches the one I have on the screen there. And as long as you're getting 50,400, then you did it right.
I should say you can also, if they're going to be working on their computer, they can plug 10 factorial divided by 3 factorial times 3 factorial times 2 factorial into Google, and Google will give them the same answer. So like the Google search understands the factorial notation as well. Okay.
Do you have to put parentheses around the denominator when you do it in Google?
Yeah, I would type it in exactly like you have in the calculator, but sometimes it's faster if you're using a keyboard.
That is definitely faster than doing it in the calculator.
Yeah. Okay, so next.
Oh, and I just wanted to, if you go back to the last slide just really fast. So obviously whenever you're permuting like letters where at least one of the letters repeats, that's kind of a dead giveaway that you want to use the permutation rule number 2. But also whenever you have a question where it mentions that you have identical objects, identical is definitely your keyword to tell you that you should use this permutation rule number 2.
Cool. Okay, so next we're going to talk about combinations. So permutations are where order matters, and then combinations are where order does not matter. And so you can think of this as like, rather than picking a president, a vice president, and a treasurer, you're just picking a committee of 3 people, and we're not assigning any roles. So when you do that, you don't need to order, or you don't provide any distinct roles, you give no rankings, okay? So the combination rule used to find the number of combinations of R objects being selected from N objects is simple. It's N factorial divided by R factorial divided by N minus R factorial. And here's a quick example. So let's calculate all the combinations of A, B, C, and D using 3 letters at a time. So we've written them out, and there are 4 combinations. And so if you use this formula, that would be 4 factorial divided by, 3 factorial, and then times 4 minus 3, which would be 1 factorial. So you end up with 4 factorial divided by 3 factorial. So that's 4 divided by 4 times 3 times 2 times 1 divided by 3 times 2 times 1. You end up with just 4. So that's the calculation there. Karen, do you want to do example 6, or do you have anything more to say about the combination rule?
Nope. So just to clarify, like, for the first combination you have there of like A, B, C. So that's like the same thing as B, A, C and C, A, B. So there's always going to be less combinations than there are permutations, because the combination kind of captures several different permutations, because the order doesn't matter that you put those letters in.
Right. We basically took the formula for NPR, and then we divided by R factorial, which is the number of different permutations of A, B, and C. You know, like if we were to write out this whole list, NPR, next to it, you'd have ABC, and then BAC, and then CBA, and CAB. And then we divided out by all the combinations of those 3 letters. And that's how we ended up with the combinations, right? Because we've just basically made all the different orderings of ABC equivalent.
Correct. Okay, so let's do another example. So example 6 says that an advertising executive must select 3 different photographs for an advertising flyer. If she has 7 photographs that can be used, how many ways can she select 3 of them? Okay, so there's nothing in that question to indicate that the order that she's selecting the photographs matters. Okay, so since the order doesn't matter, then that tells us that this is a combination. Okay, so the N is always the larger number. That's the total number of things that you're selecting from. So there's 7 total photographs, and then she wants to pick basically like 3 of them at a time. So R is going to be 3. So your notation for this is going to be a capital C, where you have the subscripts of the N and the R. So 7C3. So if we plug that into the formula, we get 7 factorial over 7 minus 3 factorial times 3 factorial. So we simplify that, we get 7 factorial over 4 factorial times 3 factorial. Write out what the factorials mean. So 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 3 times 2 times 1. And then I kind of noticed that, we had a 4, 3, 2, and 1 on top and bottom. So I crossed those out. And then 7 times, let's see, I cross the 3 and the 2 out and the 6 on top? Yeah, because those cancel with each other. So we're just left with 7 times 5 on top, just a 1 on bottom. So 7 times 5 is 35. So we get 35 different ways that she can select the 3 photographs there. Now, again, you don't have to do it out by hand with the formula. You can put this in your calculator. And you probably saw it by now if you've been playing around with your calculator. But if you go to math over probability, the third one down is the combination. So you'll see in your calculator it says NCR. So you can select that, type in the 7 and the 3, and your calculator will give you the same answer. So really the only thing you have to do is just, with a lot of these problems, is just determine whether or not it's a permutation or a combination. After you do that, then you just have to go to your calculator or Google and type it in. Yeah. So the harder part, though, is just identifying whether or not order matters. And for the most part, that just comes through practice.
Yeah, we're going to do lots of practice problems. So hopefully we'll get a hang of it by the end of this session. Okay, so in example 7, it says, in a club, there are 7 women and 5 men. A committee of 3 women and 2 men is to be chosen. How many different possibilities are there? Okay, so it doesn't say anything about roles, so I think that means that we're going to be doing a committee, we're going to be doing a combination. So again, we do lots of these problems, so whenever I see the word committee, I'm thinking order doesn't matter, let's do a combination. So we want to do 7, choose 3. So that's 7C3. That's kind of the notation for combination, is combination or choose. So 7, choose 3. So there's 35 ways to do that, because we just did that in the previous example. And then 5, choose 2 is going to be, well, 10. It's going to be 5 times 4 times 3 times 2 times 1 divided by 2 times 1 divided by 3 times 2 times 1. And when you cancel all those out, you get 5 times 2, or 10 ways. So then, because we have a subcommittee with 3 women and 2 men, we end up with 35 times 10 different options for that subcommittee. So there are 350 different possibilities for this subcommittee, or this committee containing 3 women and 2 men. Anything to add there, Karen?
Nope.
Okay. You want to say something about this?
Yeah, so that's a nice picture there of a lock. I forget, what is that lock called?
A master lock? Or a
master
combination
lock?
lock?
What is it?
Combo lock or combination lock?
Oh, combination lock. That's interesting, because we're talking about combinations. But wait a second. Combination means that order doesn't matter. And I kind of thought that when you put your code into that lock, that the order does matter.
Sure. Yeah, it does.
So what should that lock really be called?
Well, I mean, if a mathematician made it, then it would be a permutation lock for sure.
Yeah. So this is just kind of one of my little pet peeves. So obviously we all know that that is called a combination lock in everyday life, but it was clearly not named by a statistician or a mathematician, because since the order matters that you put the code in, it should technically be called a permutation lock. So whenever you see one of those locks in the future, you can kind of share that little fact with whoever is around you. Let them know that it should be called a permutation lock.
And you can think of Karen and thank her for that.
Yeah.
Okay, so now we have lots of practice problems, so we're going to go through these pretty quickly. I didn't mean to just spill that problem, so we'll just go back. So it says, Amy, Jean, Keith, Tom, Susan, and Dave have all been invited to a party. They arrive randomly at different times, and how many ways can they arrive? So I guess there are 7 people there, no, 6 people there. And so we need to do 6 permutation 6 because it says that order matters. They arrive at different times. So that's going to be 6 factorial, which is 720. Let's see.
Yeah, so there's two ways of kind of looking at that problem. You can either just say that you have 6 people and you're just like permuting the order that you're putting them in, or you can kind of view it more as like a sequence of events where the first person comes, then the second person comes, then the third person comes, and how many options you have for each of those. Either way, you end up doing some sort of calculation to give you 720.
Right. Okay. And so in part B, it says Gene must arrive first and Keith arrives last, but then you permute the other ones in between. So I look at that and say there's one person that can arrive first, that's Gene, and then there's one person that can arrive last, and so then we have 5 people left, and so we would do 1 times 4 times 3 times 2 times 1. So there are 24 different ways of permuting the rest of the people.
Yeah, so sometimes, wait, don't show that one yet.
Sorry.
I was going to say, back on part 1, sometimes they'll give you like specific criteria, and that's going to alter things a little bit. So for the most part, if they do ever like give you any sort of specifics, you probably want to stick with the fundamental counting principle, and just look at like how many options you have, you know, for each selection. Okay,
Yeah,
number 2 says that. Oh, sorry, go ahead.
I was gonna say it definitely helps to do what you did too, where you write out like bins or lines and then fill those in with the number of possibilities whenever doing these sorts of problems.
Yeah, I like doing that whenever I can. So number 2 says that telephone numbers in the US begin with 3-digit area codes followed by 7-digit local telephone numbers. Area codes and local telephone numbers cannot begin with a 0 or a 1. How many different telephone numbers are possible? Okay, so what I did was I kind of, you know, wrote out my lines that I like to use for all the different options. And then you can put a 0 through a 9, which is 10 options, in for most of the positions, except for the first digit in the area code and the first digit in the 7-digit number. So there's 8 options for the very first one, and then there's 10 for the other 2 area code spots, and you are allowed to repeat them. And then when you get to the 7-digit local number, you have 8 options for the first digit, because it's the numbers 2 through 9, and then you have 10 for the remaining ones. So by the fundamental counting principle, you're going to multiply all of those together. So 8 times 10 times 10 times 8 times 10 times 10 times 10 times 10 times 10 times 10. And you obviously get a really large number, which is good because we need a lot of phone numbers. So,
yeah.
Oh dear, what is that number?
Well, it's 64 times that many tens. So that's what, 6.4 billion is what I would call that.
Yeah.
Cool. Okay, so now problem 3 says how many different 4-letter codes can be formed if the first letter must be an S or a T and you can't use the same letter twice. So I'm assuming we're using the 26-letter alphabet here, right? And so we have S or T are only 2 options for the first letter, and then it must go 25 times 24 times 23 because we can't use the same letter twice. So as soon as you use S or T, that must go there. And then we can use any letter we want, but we can't use the S or the T that we used in the first place. There are 25 options for the second letter. And then because we've used 2 letters, there's only 24 options for the third, and then 23 options for the fourth letter. So there are 27,600 codes, just like a number of different like passwords or something if you had a 4-letter password.
Yep.
Okay.
Okay, number 4 says 4 bands and 3 comics are performing for a student talent show. How many different programs in terms of order can be arranged? Okay, so all in all, we have like 7 different acts, and we just need to figure out the different orders that they can go in. So you could view this as like you have 7 things and you're permuting all 7 of them, so 7p7. Or you could think of it as like a sequence of events where you have to choose who comes first, who comes second, who comes third. Either way, you're going to get 5,040 for your answer there. Okay, so then part B, now we're kind of getting some specifics. So now it says how many different programs are there if the comics must perform between bands. Okay, so it has to go band, comic, band, comic, band, comic, band. Okay, so if you think about the ways you could do this, well, who's going to be the first band to perform? Well, you have 4 different bands that you can choose from. Okay, then the comic, it has to go next, and there's 3 of those that you can choose from. Since you've already selected a band, you now have 3 bands to choose from for who goes next, and then 2 comics remaining, and then 2 bands, and then you're left over with whoever the last comic is and the last band is. So you'll multiply 4 times 3 times 3 times 2 times 2 times 1 times 1, and you end up with 144 different programs.
Cool. Okay, the Hawaiian alphabet consists of 7 consonants and 5 vowels. How many 3-letter words are possible if there are never any consonants together and if a word must always end in a vowel? I'm gonna have to read that one again. So we have 7 consonants, 5 vowels, and we're just saying words are just any arrangement of letters.
Yeah, it doesn't actually have to be a word.
Right. If there are never any consonants together and if a word must always end in a vowel. So we always end with the vowel. So the vowels, there's gonna be 5 options at the end, right? And there are never any consonants together. So that means that the consonant either goes at the beginning or in the middle, right?
Okay, so you could have vowel, consonant, vowel, or consonant, vowel, vowel.
Right, and that's it.
Is there any other option?
Well, it says it must always end in a vowel, right?
Okay. Does it say that there has to be a consonant?
Oh, so you go vowel, vowel, vowel?
Yeah, so there's actually like 3 different arrangements, I guess you could say.
You add up each one of those possibilities. So you multiply, so you get 5, 5, 5 for vowel, 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 and then 5, 7, 5 for vowel, consonant, vowel, and then consonant, vowel, vowel. So 475 words total. So I think that just shows you, like, in these combination permutation problems, they're kind of fun once you get the hang of them. But they're always a challenge because you got to read the problem and really kind of sort out what's going on. And like I said, sometimes it's good to do these with teams or something. Talk it over with the neighbor, make sure that you're interpreting the problem as it's written. Because if I had just answered that by myself, I would have just said vowel, consonant, vowel, and consonant, vowel, vowel, and I would have left off vowel, vowel, vowel if Karen hadn't checked me.
Yeah, I would say that's actually one of like the hardest problems in this section, but that's why I make sure that we kind of do it together on here. So you've at least seen it before you get it on Connect Math.
Right, cool. So this is a Connect Math problem.
I think so.
All right. You want to do 6?
Sure. So it says a phone company offers 6 models of phones, each in 4 different colors and each with any one of 5 data plans. How many combinations are possible? Okay, so I've got 6 different phones, 4 different colors, 5 different data plans, and I have to choose one from each one of those. Okay, so hopefully this, kind of sounds just like the soup and salad thing. Okay, so all you have to do, according to the fundamental accounting principle, is just take the number of choices that you have for each category and multiply them together. So we have 6 options to choose from for the model, 4 for the color, 5 for the plan. So 6 times 4 times 5 comes out to 120 different combinations.
Great. So let's see, the next one. We have how many different ways can 4 tickets be selected from 50 tickets if each ticket wins a different prize? And so the fact that each ticket wins a different prize tells me that they're all individual tickets, right? I mean, there's 50 individual tickets.
Yes, but the order that you assign the ticket with the prize matters.
Okay.
That's the key here because they're different prizes.
Okay. So since the order matters, then it's going to be a permutation.
Yeah.
So it'll be 50P4, which I'm not going to do that one by hand. I'm going to plug that into a calculator for sure. Do you want to do 8?
So does that make sense? Let's just clarify that. So since it's different prizes,
Mm-hmm.
that's the same thing as order mattering.
Okay.
I don't know a better way to explain that.
I mean, it could be more,
Okay,
it could be more explicit about order mattering, because I would be tempted to say it's like, oh, 50 choose 4 because you're just picking 4 tickets.
but think about it. Like if you have a group of 4 people
Mhm.
and everyone's getting a different prize, then couldn't you permute those 4 people?
Oh, absolutely. No, if it's 4 different people, like if you're doing a raffle or something, and then that makes sense to me. But it's like if I'm just picking 4 tickets out of a hat, I think of that as a combination. So I guess that's where I'm getting tripped up.
Yes. So I did not write these questions. These questions are written or copied directly from the book.
Okay.
And some of them are like kind of terribly written.
Yeah, I mean, just a little vague, but I can see how that, once you give me that interpretation of you have different people, each one has a ticket, then it makes sense to me,
Yeah.
right?
We'll make sure that like on any sort of assessment, as far as like quiz or test, we pick the problems that are more clear.
Right.
I do always promise that to my students.
Good.
Okay, so number 8 says, how many different ways can 6 identical hardback books, 3 identical paperback books, and 3 identical boxed books be arranged on a shelf in a bookstore? Okay, Dr. Rinsko, do you remember what the word identical was a key word for? Which rule?
Right, that's permutation rule number 2. So we have like R1 would be 6, R2 would be 3, and R3 would be 3.
Yeah, and how do you figure out what n is?
Add all those up. So that'd be 6 plus 3 plus 3 is 12.
Yep. So n is 12, and then your r's are the 6, the 3, and the 3. So you just have to figure out 12 factorial divided by 6 factorial times 3 factorial times 3 factorial.
Mm-hmm.
And you get 18,480 ways.
Cool. All right, 9. How many ways can 4 baseball players and 3 basketball players be selected from 12 baseball players and 9 basketball players? So here it doesn't say that we're giving them positions or anything. We're just picking 4 of them. So I would say that that would be 12 choose 4 times 9 choose 3. So that's 495 different ways of picking the baseball players and 84 different ways of picking the basketball players. And then you multiply those together, you get 41,580 different ways.
Yep.
Okay.
Okay, you and 19 of your friends have decided to form a business. The group needs to choose 3 officers. Okay, so we have distinct roles here of a CEO, an operating manager, and a treasurer, and how many ways can those offices be filled? Okay, so we're not just picking them for like a committee where they all have the same role. We have distinct roles now, so this is where order is going to matter. So when I did this problem in a previous semester, I did 19 P3. And a student very nicely corrected me. Can you tell why that's wrong?
Because you and 19 are your friends. So there's...
Yeah, so you got to read carefully. So it's you and 19 of your friends. So really there's 20 people total that you're permuting. So 20P3 or 20P3. Or you can kind of view it as like you have 20 people to choose from to be the CEO, then you have 19 people to choose from to be the operating manager, and then 18 for the treasurer. Either way, though, you should get 6,840 ways.
Yeah, I mean, I've done things like that too when people ask me how many siblings do I have, and I just say how many kids we have in the family, or vice versa, so that's a common. Yeah. Okay, so 11 says that there are 3 roads leading from Cape Coral to Fort Myers, 4 roads from Fort Myers to Estero, and 6 roads leading from Estero to Naples. So how many ways are there to get from Cape Coral to Naples? So here you have to kind of know a little bit about our local geography, but basically it goes Cape Coral to Fort Myers down the coast, and then Fort Myers down to Estero, and then Estero down to Naples. So we're looking at 3 times 4 times 6, because we're going from Cape to Fort Myers to Estero, and Estero to Naples. So 3 times 4 times 6 gives us 72 different ways that we can get from the Cape down to Naples. Is this like, did you make this up?
I did write this question myself, yes. Okay. Well, I just changed it. It had like cities that I didn't know what they were, so I just changed the names of the cities.
Cool.
But yeah, the idea is that you have 1 road to choose from between each city. Mm-hmm. So. Okay, 12 says you volunteer to help drive children to a zoo, but you can only fit 8 of the 17 children in your van. I just think this is such a weird question. How many different groups of 8 children can you drive? So how many ways can you put
7.
8 children out of 17 total into your van? Okay, so there's nothing really in that question to say that like the order matters, that you're actually putting them in the van. You're just kind of throwing them as a group into your van. So order doesn't matter. So this will be a combination. So n is always the larger number. So 17, C, 8. And you get whatever that works out to. I don't know.
24,310 different groupings.
Yep, that's a lot of different groups.
Okay. Okay, so you are taking a multiple choice test that has 6 questions. Each of the questions has 4 answer choices. If you select one of these choices for each question and leave nothing blank, in how many ways can you answer the questions? So now we have 6 questions and we have 4 different options for every single one. So that's a 4 to the 6. So this one's not a permutation or combination. This is only using the fundamental counting principle. Right, so there's 4,096 different ways of answering that test or filling out that test. Do you want to take 14?
Sure. So in how many distinct ways can the letters of the word Mississippi be arranged? Okay, so whenever you're arranging letters in a word, you know, that's that permutation rule number 2. So you'll just figure out like how many of each letter there are and how many total letters. So for Mississippi, let's see, there's 11 total letters, and then there's 4 S's, 4 I's, and 1 M, and 2 P's. So you get 11 factorial over 4 factorial times 4 factorial times 1 factorial times 2 factorial, which comes out to 34,650 ways.
And then 15, it's how many different ways can you watch your favorite 4 movies on Netflix? So you have 4 options for the first one, 3 for the second, 2 for the third, and 1 for the fourth, or 4P4, which is 24 different movies. And these just keep going, Karen.
I know, we're almost done. 3 more. So in 2011, the US Senate consists of 51 Democrats, 47 Republicans, 2 independents. How many distinct 5-person committees can be formed if each committee must have 3 Democrats and 2 Republicans? Okay, so we need to pick 3 Democrats out of the 51, 2 Republicans out of the 47. So both of those are just going to be combinations because it's just like generic committees without distinct roles. So you'll figure out 51C3 and 47C2. And then each one of those, you know, committees of Democrats can be paired with each one of the committees of Republicans. So you've got the 20,825 choices for the Democratic committees. And we're going to multiply that with the 1,081 different committees that you can make from the Republicans. So that's like the soup and salad thing again, only now it's Democrats and Republicans. So you'll multiply those values together and you get 22,511,825 committees.
I think that this is an example where you see like, maybe it seemed confusing why we were doing 4 choose 3 or 4 choose 2. But when you see these really huge numbers, it's so much easier to say 51 choose 3 times 47 choose 2. And any mathematician around the world knows exactly what you're talking about. You're counting up the number of combinations. So sorry, I went on a tangent, but when I see numbers like that, I just can't believe that no one like that. I mean, everyone uses this that does any type of counting problems, but it's always scary at first, I guess. Okay, 17. In a race in which 8 cars are entered and there are no ties, in how many ways can the first 3 finishers come in? Okay, so there are 8 cars, and there are no ties, and we want the first 3 finishers. So that's going to be, order's going to matter. So it's going to be 8 times 7 times 6, or 8p3. So 336 different ways.
And then our last one says that from 10 names on a ballot, a committee of 4 will be elected to attend a convention. How many different committees are possible? So by now we know, a general committee is just a combination. So 10C4 gives us our answer of 210 committees.
Great, thanks. Sorry, I got tongue-tied there at the end, but there's so many examples.
Practice makes perfect.
It's true. And we were doing some of those on the fly, so I was like trying to think and talk at the same time. That's tricky. Okay, well, that was great.